Swayam Prabha. Digital India. Educated India.
Hello everyone. So today we are starting the second chapter. So the chapter is Divide and Conquer. So what is this about? So in the last week we talked about complexity analysis. So you know how you can analyze algorithms in terms of which algorithm is more efficient than another. Okay, so finally it gives me what is a more efficient algorithm. So that was a generic thing that we will use throughout this course. So we will talk about algorithms and we will talk about the complexity analysis so that we can finally understand which one is a more efficient algorithm. So but how do we come up with an algorithm? How do we design an algorithm, and what are the thought process that would go behind it? Okay, so there are various techniques for designing algorithms. So you can call them some algo design techniques. And in this course, we talk about three of those. So there is divide and conquer, there is dynamic programming, and there is greedy. Okay. So till now, you would have encountered with various algorithms in this category already. So you have already worked on certain algorithms that are divide and conquer. You may not know that they are divide and conquer. So we will formally study those. Okay, and these two will be quite new: dynamic programming and greedy algorithm. But overall in the course, we are interleaving algorithm techniques and the data structures. Okay, so you will see that today I will talk about algorithm technique in this week. In the next we will talk about the graph data structure. And we are interleaving these, so you get a flavor of both data structures and algorithm techniques today. So so let's start with divide and conquer. Okay. So what is the basic framework of divide and conquer? So the name says a lot, divide and conquer. So what do we do here? So suppose you want to solve for a problem for which an input instance of size n is given to you. Okay, for example, say you are given a sorted array, size n, okay, and the problem could be find the element with key x. Say if we are all integers, say something like find an element, so find an element with key 20. So it's an element that's value is 20. So you have to find the sorted. So you are given input instead of size. That is fair. Now to solve this problem, what you do this divide and conquer. Okay. So by the way, the name would be very familiar, divide and conquer. Okay. So in our history, we talk about divide and conquer. So you are solving this problem by the same strategy. So you want to divide this problem of multiple smaller instances and then solve them, and that's how you conquer the larger instance. So you do a divide, that is break the problem instance into subproblems. So what are the subproblems? They are instances of small instance. Okay, and then you conquer this. That is, now you will, so you're dividing the whole problem into smaller subproblem, and then you want to conquer it by recursively calling. So recursively call the algo on each of the subproblems. And when you're recursively calling, you're again dividing them into smaller problems. And when do you stop? So you stop when an instance is sufficiently small. You stop. But yeah, so where does the algorithm end? So you divide into smaller problems. You're conquering it by keeping on dividing into smaller problems. But then comes the main step that is called combine. So now you had a larger problem. You tried calling the smaller instances from there. So from the large instance, you tried calling the smaller instance, and the smaller instance will give you the output of the smaller instances. Okay, so you have to, so the recursive calls output the solution to the subproblems. Now you have to combine these solutions to obtain the solution of the original problem, that is of instance. So okay, so you see there are three many steps. So there is divide, there is conquer, and there is combine. So any instance where you can apply these three strategies, divide, conquer, and combine, we will apply this algorithm. So first of all, let us try to see, are there some problems that you have already done where you are applying this divide and conquer. So let's try to see certain examples. So what is the first thing that comes to your mind where you did this divide and conquer? I already gave you the example problem. So why don't we talk about binary search? Binary search. Okay. So binary search runs on an array. It's a sorted array. Okay. And we need to search for a key. So search for 8. So binary search has also been covered in the previous chapter. So you know what you do. You find out the middle of the array. Yes, see if this number is greater than equal to or less than that. If you find the middle element is larger than this search key, then you will search in the left. Otherwise, you will search in the right. Okay. So what is happening? So you're dividing the original instance of size n. You see, originally it is of size n. You're dividing into subproblems of size n by 2, n by 2. Okay. So this is the conquer step. Now again you divide into n by 2. Again you go to the middle element and see whether you have to go to left or right. So again this n by 2 will go into n by 4, n by 4, two subproblems. Then you will go to only one of this. Okay. And what is combine? So you are recursively calling the subproblems and by the 10 by 4 and so on. So these will return you the solution. In this case, the combine is very trivial, so you don't have to do anything. At some point, you either find the solution or you say, okay, I already exhausted my search, so I can't find the solution. The element is not in the array. So combine is trivial here. So divide is simply dividing. So you compare with the middle element, that is divide. Compare with middle. Conquer is you recurse into one of the subarrays. One of the subarrays. And the combine is trivial. So now, once you understand this is actually divide and conquer algorithm, now the next point is how do we understand what is the complexity of this? So for understanding complexity of the divide and conquer algorithm, you will need to write some sort of recurrence relation. This is like an all-time analysis. Okay. So how do you write a reconciliation? So reconciliation, you say what is the complexity for each problem instance of size n. Okay, so that is Tn. And how do you write it? So you say you are first of all what you are doing, you are comparing with middle element, that is a constant time operation, order one. Then you get two subarrays, but you go into one of them. So you are actually recursing into subarray of size n by 2. So that is Tn by 2, only one of this. You don't go to both the subarrays. You only need to go to at most one subarray. Tn by 2 plus order. That is your reconciliation. Now, how do you solve for this? I think you have tried something in your tutorial, but let's just do that for the sake of completeness. So you say, okay, Tn is Tn by 2 plus order. Sure. So we are trying to create a tree, and every node in the tree is some sort of, every leaf in the tree is some sort of time that you're doing. So order one is time that you're doing. But Tn by 2 you're further dividing. So you are going to sum. You are going to in subarray of size n by 4 and you're doing order and time operation. This is time that you have already spent. Again, you go to an array of size n by 8 and you spend it at order. And you keep on doing that. When do you stop? When the problem instance is of sufficiently small size. So that means you are only at one element. So suppose at some step Tn by 2 to the power k. You cannot go any further. Then there is also an order. Okay. So that's where you stop. And what will be k? Now k should be such that you cannot go further. So k in this case should be log n. Okay. So you cannot do 2 to the power log n, you will take 9. And so fine. So that is like, so this becomes T1. This becomes T1. And imagine T1 will take some constant time. That is solving for a problem of size 1. Only one element, you have to search for the key, it will take constant time. But then you did some other work. This order one works you have done multiple times. So how much overall work you have done? So that will depend on what is the depth of this tree, or what is the height of this tree. So how many times you have done this order one work? So you see you have done for n to n by 2 you have done once, n by 2 to n by 4 you have done once, overall twice. So up to here you have done k times. So your work is k times order 1. Okay, and what is k? K is log n. So you say your Tn is order of log n. That is the complexity of binary search. And I think you already know this. The binary search takes log n time. And now this is interesting. So I have a sorted array. I have to search for a key. I can do that in order log n. Now, this is a problem that you all know. But interestingly, this can help you in solving many other problems. You may see some in your assignments as well. So you can see things like, okay, I have a sorted array. So 3, 8, 10, 12, 18. And suppose I say shift all the elements in cyclic manner. So cyclically shift all these. Okay. So suppose something like 3, 8, 10, and then 12 and 18. So cyclic shift. And suppose you are given only this array. Okay. And your task is to now find out at what index you did this shift. So you can again think of this, okay, can I do binary search and solve this? Because otherwise doing it linear time will be order and complexity. You don't want order and complexity. Binary search, a divide and conquer approach gives you order, log, and complexity. And like that, there are many other things that you can try solving. Let's see some other example. Again, a simple problem. Suppose you talk about powering a number. So what is it? So you are given a number x and an integer n greater than or equal to 0. You have to find x to the power n. That is the problem. Now what is the simplest way you will do that? So the naive algorithm. So generally we talk about naive algorithm to set a baseline. Okay, if you don't think in terms of design technique, what is the simple algorithm you will come up with? So naive algorithm in this case would be, I'll take x, multiply with itself. Yes, whatever resultant I get, I multiply with x again I multiply with x, and so on. Okay, so you are doing n minus 1 times your multiplication. Okay, so this will be a theta n ordering algorithm. Not very good. Yes, this is naive. So generally, naive algorithms are not very good. So can we do something smart? So can I use divide and conquer? So can I use divide and conquer to do something? And you will think, okay, I have to use divide and conquer. So I have to power x by n. You have to power x n times. Okay. So okay, can I divide that into smaller instances? And very often you see the small instances are like typical use cases, they are roughly of same size. So okay, can I divide into two instances of the same size? Sure. In this case that looks easy. So can I say this should be x n by 2 n by 2. But then you say okay, no. N by 2 whatever is related should be an integer. Now if n is odd, this will not be an integer. So then you say okay, fine. I'll make two cases. So I'll say xn would be xn by 2 times xn by 2 if n is even. Then this will be xn minus 1 by 2 times xn minus 1 by 2 times x if n is odd. That way I am satisfied. Okay, fine. Now this thing is an integer. Okay. So that means this itself is an instance of a problem. So I have this follow instance. And do you see something like binary search that although you have two instances, you have to go to only one of this? Yes. So what you can see here, so both the instances are same. So you have to find out xn by 2, and the second thing is also xn by 2. So you can just multiply with itself. Okay. So that means you have to only compute one of this, and then multiply some order one. So the complexity will be Tn, which you take one instance n by 2 plus order. And then you can use the same solution we did for binary search and say, okay, Tn is order log n. So your login is a very interesting term you will see in many of the divide and conquer algorithms. So many times you divide them into two instances and only have to go to one of this, and then immediately the complexity is order log. Let's see some other. So yeah, so we will now see some other problems that we have already encountered before, and now we will go from search to some sort of sorting algorithms. Okay, so we talked about algorithms such as search and powering a number. Okay, so now let's talk about some of the sorting algorithms that are again based on divide and conquer paradigm. So we'll talk about some sorting algorithms. Now, what are the sorting algorithms you know are divide and conquer type? So, merge sort and quick sort are some of the most popular ones that are under this category of divide and conquer. Now, how do you see divide and conquer in this? So actually, it's very easy in merge sort. It's a very interesting thing on. This is like a standard example for divide and conquer. Okay, so what do you do in merge sort? So your problem is you are given an array of size n. Okay, so n elements, and you have to sort that, right? So increasing order, decreasing order. So say increasing. So now what is the algorithm? So if n is 1, so you are done with the base case. So otherwise what you do, you recursively sort. A 1 to n by 2 and a n by 2 plus 1. Okay. So you're sorting these two. So this is like you are taking your original problem of instance size n, divided into problem of smaller instance sizes, n by 2, n by 2. Now you recursively sorting. And you keep on doing the same, keep on recursive while you are trying to sort this, you will again break into n by 4, n by 4. But at some point of time, you will get the solution back. So that time, because you have to sort the entire array, so there is also a combined phase. So combined phase was sort of missing earlier. So this is the divide and conquer. So you are dividing into two arrays. Conquer, you are recursively calling this. And they will be combined because you get the solution for this part. So the solution for this with the solution for this. And you have to combine this. And this combine happens by merging. So you have to merge two sorted lists into a single sorted list. So that is the combine phase. Okay. So here in this you get all the three. You get divide, conquer, and combine. So quickly how this looks like. So suppose you are given the sequence of, there are 8 integers, and you divide this array into size of 4 each. Yes, keep on dividing until the problem instance is of very small, like sufficiently small, this is size 1 only, but you cannot divide further. And at that point you start coming back. So that is you merge. So you have these solutions, you merge them. So this gives you 27, this gives you 20. Again you merge this. So remember from here you called this and this. Now you got the solution. And you have to go back here in this call so that you can merge this to the final solution. So this is now sorted list. Similarly here you get the sorted list. And again in this call where you divided, you go back and merge this. So this is your final. So this is the merge sort paradigm. And you can very quickly write a pseudo code if you want. So the main program is very easy. You have to call merge sort again twice, okay, and finally you have to merge the outputs. Okay. So that's all you have to do in the main function. And separately you have to write the function for merge to list. So now, so if you want to write a pseudocode, that will be first you talk about the base case, then you talk about call with 1 to n by 2. Second, you call with n by 2 plus 1 to n, and then you can merge the outputs. Okay, so now let's try to do the complexity analysis for this merge sort algorithm. Okay. So what we did, we took an array of size n, divided into two sub-arrays of size n by 2. Remember now, unlike binary search, you have to call merge sort in both of these. Okay, so you have to use both of these sub-arrays. And there is a combined step also. We are taking the solutions and merging this together. So what is the overall time? So suppose Tn is the overall time. So you say, okay, I created two instances of size n by 2 plus I am doing a merge operation. What is the complexity of merge operation? So you're taking two instances of size n by 2, merging them to create a sorted list. Okay. Now merging, so you have two sorted list as input and you have to create a sorted list as output. So it takes order and time. So because what you will do, you have two sorted list as input, say n by 2, n by 2 size each. You have to create a single sorted list of size n. So what you will do, you will keep the pointer to the first element, choose which one is smaller if you are doing increasing order. So this is smaller, 3 and 7. So you will choose this. Then you will put it here and again compare. Suppose this is smaller, you will now take this and so on. So what you will see, you will have to go to each element once and every time you move one element. So you will take order and time. So merging will take order and time. So you take fine. And remember in binary search we had only one. We have to go to one subarray. Here you are going to both the subarrays. So now you try to expand this. So this will be 2. Now Tn by 2 you will again say 2T n by 2 square plus order n. Okay, let's write order n as something like Cn. You can always find some C as that. Yeah. Okay. So, so this can be C times n by 2. And this Cn is always there. And from here, you try to keep expanding this. So anyway, you can expand this term. This will give you 2 square T n by 2 square plus Cn. There is one Cn here, another Cn here, 2 times. Now again you take arrays of size n by 2 square and continue doing that. So you will stop when n by 2 to the power k becomes of size of t1. So this k is log n. So this will go to 2 to the power log n t1 plus, and there will be k terms here. So this will be Cn log. Okay. And in other words, that is Cn log n plus t1 is constant. So you have n times t. And this together give you a complexity of theta and log. And this is in all time. I mean, this is both. This is work for worst case, average case, best case. This would work for all of this. So this is the complexity of merge sort. So by the way, I hope this is clear, but I still want to tell you that we talk about tree analysis, right? So we talk about worst case, best case, average case. Sure, maybe let me write best case approach. We also talk about something called an upper bound. Yes, tight bound and a lower bound. So do you think there's any connection between this? So this is a lower bound. So can I say that best case corresponds to lower bound and worst case corresponds to upper bound? Can I say something like that? What do you think? So actually many students have this confusion that worst case is like upper bound and best case is like lower bound, but no. So they are all orthogonal things. They are orthogonal things. So in worst case, you can talk about all three. What is the upper bound, what is the tight bound, and what is the lower bound. So in worst case, so you will come up with a term, something like Cn log n, and you can say, okay, this is order of something, this is theta of something, this is omega of something. So you can say that. So you can do this, so you can do all three for all the three cases. So do not confuse between okay, worst case is same as upper bound. Yes. Now going back, so we found that merge sort has a complexity of theta and lambda. Now what about quick sort? Now quick sort, so you might remember quick sort. Again, very interesting idea. So you have an array of size n. Now how do you apply quick sort? So you will choose an element as the pivot. So you take say first element as a pivot. And you rearrange, so choose x as pivot and rearrange A such that x is put in its proper position in the sorted array. So x is put in its proper position in the sorted array. So something like, okay, so all the elements of the array, you think of it as 2 blocks or 3 blocks. So x will be somewhere in the sorted position. Another, there will be elements that are less than equal to x. And other elements that are greater than x. Okay. So you think of dividing this in that. So everything to the x, left of x will be less than equal to x, and everything to the right is greater than x. But these may not be sorted. So that is the idea. So you choose a pivot and rearrange A such that x come in its proper sorted position. So now you know, now you have two subarrays, and you can recursively sort this because x is in proper position. So you sort from here to here and here to here by the same logic. You can recursively call this on both the subarrays. So this is your conquer step. So this is your divide step. So find the proper position for x. That is your divide step. Then conquer is you try to recursively call on both the subarray plus form. And there is no combine. So combine here is trivial. So this is interesting. In the merge sort, combine was not trivial. In combine it is not enough operation. But the divide was trivial. In divide you just take n by 2. In quick sort, the divide takes time. So you have to put x in the proper position. And if you want, you can quickly check how much time. So let's write down a quick pseudocode for this. So you have this quick sort, and you need the array, and you need the start and the elements. So what is the base case? So if there's only one element, if the start is equal to end, you return. Now you have to make a partition into two subarrays. So for that you have to call a routine. So find index I, that is partition. Call this function partition. You give a start and end. So inside the partition function, it will choose something as pivot and choose the first element at the pivot and find out what will be its position, final position. And once you know I is the position of x, okay, then you can call quicksort accordingly. So quicksort, once you call on a, say it remains the same. Now first time you call start to I minus 1, and second time you call on a from I plus 1 to 1. And that's all is a quicksort. So you have to just define the partition. Now what happens inside the partition function? So you have this partition function where you give the parameters array A, the start and end. Now what you do is assign x as the A start. The first element, we call it x, that is a pivot. Now you create, so let's take an example. So suppose you are given an array, so it initially will be given an unsorted array, and the elements are 6, 5, and 7. 6, 10, 13, 5, 8, 3, 2, and 11. So these are the elements. So how do you start? So you are given, this is your x. Okay, this does not change. So this is your x. And you initialize two indices. That's what you will be using. So you have index I. So that is the start. So this is your I. And you have another index j, that is start plus 1. So this is your j initial. Now, and these indices will move. Okay. So now it should be, so you should understand what do these indices denote. So so generally, so what happens, so I start, so I indicates the boundary up to less than equals to x. So then that means starting from x, so you are processing. So generally in the array, the first thing will be x, and at some point of time, up to some place, all the values will be less than equal to x. So that's where you'll put your I. Okay. And similarly, j will mark the boundary after I, starting from I up to j, all the elements will be greater than x. And to the right of j, all of these are unprocessed. So you are about to process this. You have not yet processed. But up to here, you process and divide into two boundaries. This is x, this is less than equal to x, this is greater than x. And that's how the boundary moves. So this keeps on moving. And slowly, at the end, what will happen? You will have x less than equal to x and x. And that's where you will have the I. And at the end, what you will do, you will simply swap these. So this element is anywhere less than equal to x. So x comes here. Everything to the, so what will happen now after you swap? X will come here. X will come here. And all this will become less than equal to x. And this is equal to x. Okay. That's how the algorithm will proceed. Now the question is, okay, how do I move the indices? That's quite easy. So you start with I and j. Okay. And you see, j will indicate all the elements that are greater than x. Okay, so as long as you are finding that, so you move forward, so move j forward until you find something like aj is less than equal to x. So that is fine. So I can keep moving j, yes, greater than x, not a problem. J. Now you find something that is less than equal to. So that's where now what you should do. So it cannot be, this element cannot be j. So this cannot be in this boundary, right? This is less than x. So what you do is something interesting. You say, okay, I have to maintain a boundary without doing too many changes. So I know that the indices that is starting this j boundary, this particular index, this value is larger than x. Okay, and this value I found to be smaller than x at this point. So what I will do, because I can now increase this boundary, so going up to here, put I here and swap this value with this one. So in effect what would happen, this boundary will increase by this much, everything will be less than equal to x, and from here to here things will be larger than x, and that will be resolved. So in the picture what will happen now, I'll take I to here, okay, so this becomes my I, and I swap this with this, 10 with 5. So now, so this value will be 6 and 5, I is here, then 13 and 10, j is here. So you see, up to I values are less than equal to x, and after I up to j values are greater than x, and then there is unprocessed part. So what I do, move j forward until I find aj is less than equal to x, then I move I forward by 1 and swap. So you see ai and aj, you swap. So now you have your new I, your new j, and continue like that. So you will go forward with j greater than x, nothing to be done. Again go forward with j less than x, so you swap. How do you swap? You first move I and then swap this with this. So what will be the value now? 6, 5, 2, 10, 8, 13, 2, 11. Okay. And similarly now your I'm sorry, 8, we have gone up to 3, yeah, that's fine. So yeah, what you change is 3, not 2. Yeah. So this should be 3. Okay, and your I is here and your j is here. Either you go forward, and that time you will replace this 2 with 10, and yeah, that will be the final thing. Last value is greater than x. So your overall array becomes 6, 5, 3, 2, 8, 13, 10, 11, and that's where your I is, and that's where your j is at the end. And because j reaches the end of the array, you stop. But now, is this the final output that you need at this point? Remember, you want to keep x in its proper sorted position. Okay, and what should be right? That should be this, ith index. So what you do now, you will swap a start with a. So you swap these two. So your final array becomes 2, 5, 3, 6, 8, 13, 10, 11. And as you can see, these values are less than equal to x. This is x, and these are greater than x. And that is as a result of partition algorithm. Good. Now, so this was the divide part. You see, you have divided the array into 2 sub arrays now, and then using this
quick sort, that the conquer part, you will go individually to each of the subarrays and recursively call the same thing. Okay. So, and you see the combine is very trivial. Once you get the output of this will be in its sorted position, this will be sorted, and this is anyway in the sorted position. The whole array will be sorted once you get the solution for this. So good. So now we talked about divide, conquer, and combine is trivial. So let's think about what will be the time complexity of quicksort. Sure. So let's write the all case complexity Tn. Now, so what are the things we did? We did a partition. So what is the complexity for partition? So this partition algorithm, so we are maintaining two indices I and j. Every time we are moving j by 1, except when we find something less than equal to x, in that time we swap, but we swap only once. Okay, so that means at most we will move n times and do n swaps. So this the complexity will remain phi time for partition. So phi time for partition. So there is a theta in complexity plus. Now you are doing the conquer part. You are recursively going into two subarrays. Now let's see what are the complexity for both the subarrays. Okay, now this is where it is different from merge sort. You see the two subarrays need not be equal in size, like need not be roughly n by 2, n by 2. And what will this depend on? So let's say this is the index I. Okay, so what will be the sizes of the two subarrays? This will be I minus 1 and this will be n minus I. Right? So I minus 1 plus 1 plus n minus I becomes n. So that means the two arrays are maybe on different size. So theta n plus t of I minus 1 plus t of n minus n. Okay, now how do I solve this? Good. So before I start solving this in detail, let's do some simple things like, okay, what will be the worst case analysis? Like what will be the worst time this can take? So you see what is happening. So here Tn is theta n plus Ti minus 1 plus Tn minus n. So as long as say one of so you see, if in divide and conquer what you do, you try to divide into multiple subproblems and you try to ensure that their sizes have become smaller. Say if this becomes n by 2, this becomes n by 2, you are happy. Okay, I divide into subproblems, each of them is much smaller in size. But on the other hand, suppose this does not happen. So the worst case, what can happen? The two sizes become 0 and n minus 1. So then you are not gaining much. You are just saying, okay, I am just removing one element at a time, and you have to go to a subproblem that is n minus 1 in size, and that is where the divide and conquer may not be very helpful. So first of all, let us see whether this will happen in this case. That the two subarrays, one is 0 in size, another is n minus 1. Can this happen? So this can happen when there is no value that is less than equal to x after x. Now when can that happen? In an array, x is the smallest, everything is larger than that, and that will happen always when this is sorted in increasing order, right? So you will start here, j is here, every time you go j just keep on increasing, there is no swap happening. So there is no second array, there is only this array of size n minus 1. Now you can analogously find the other case when this will happen. So this will happen when this is sorted in the decreasing order. That time this will be so x is the largest value and everything is smaller than x, n minus 1 and 0. So in both the cases when it is sorted either in increasing order or decreasing order, you will find they will be very skewed. The partition will be very skewed. And the intuition we were talking just before is that if this is very skewed, divide and conquer will not help much. It will not be very helpful. And let's see, let's try and solve this. Okay, so in this case what will happen? Tn is theta n plus t of n minus 1. T of 0 we are removing. T of 0 is, let's say it's 0. Okay. So how much time it will take? Now theta n, you can say something like Cn. Okay. Generally, whenever it is theta n, we can always say, okay, this is something like Cn. You can also think of it something like theta n is less than or equal to some Cn. Okay. So now let's see. So Tn is Cn plus T of n minus 1. Continue. T of n minus 2 plus Cn minus 1. So it comes Cn plus C of n minus 1 plus you again further subtract 1 n minus 3 plus C of n minus 2. And you keep on doing that. Okay. So what will happen? C times n plus n minus 1 plus up to 1. Okay. And the term becomes like T0, and that's what you ignore. Okay. Now this is the complexity, and you know this series, so this will be C times n plus 1 by 2. Right. And what is that in terms of order? You can write it order n square or theta n square. Now this is bad, right? So why do we have to do this slightly complicated quick sort? I could have done this with insertion sort or bubble sort, right? They would have given me theta n square. So yeah, this worst case complexity is not good. Worst case is theta n square. Sure, fine, but that is just worst case, right? So let's see what is the complexity of quick sort in an average case. So what is the average case and complexity? So how do we do average case? So what do we have? We have Tn is some Cn plus T of I minus 1 plus T of n minus 1. Okay. Now how do you even start talking about an average case? Now what is average case? See, you can do an average case over what? So you have this array A, and you start the initial element as x, and you transform into another array in partition case, we are less than equal to x, and greater than x. So the two partitions depend on what will be the index of I at the end finally. Yes. So the average case has to be on this index of I. Now this index of I, what are the values it can take? It can go from 1 to n. It can take any of the value in the final sorted array, right? X can be anywhere. And for this average case analysis, what we will have to assume, we have to put some probability distribution over all these possible positions. Now we don't have any other prior knowledge, so we will say, okay, let's assume all these are equally likely. So that means there is a probability of 1 by n for each of the position. Okay, good. So once I put that condition over here, now you can say what will be the Tn in average case. I will still write Tn, I am more comfortable with that, but this is the average case analysis. Okay, so I am doing that on the new page. So your Tn will be Cn plus 1 by n sigma I is equal to 1 to n T of I minus 1 plus T of n minus I. Right? I'm sorry. Yes. Now this is what this Tn will look like. Now how do I, okay, some things I can do quickly. So for example, I can simplify this term. So what will be this? Sigma I is equal to 1 to n t of n minus I plus t of I minus 1. So what would happen if I start putting I equal to 1, I will get t of n minus 1 plus t of n minus 2 up to t0. Similarly in I minus 1 I start putting I, so t of 0 plus, and when I put I equal to n, t of n minus 1. So that means the same term will repeat, so they will come twice. Okay, and this I will ignore. So this will give me 2 times t1 plus up to t of n minus 1. Okay. So this is where I will simplify it. So my Tn now is theta n plus 2 by n. I am putting this back here. Sigma I is equal to 1 to n minus 1 t of I. Now still this is not in a form that you can solve easily. Okay. So Tn is in terms of n minus 1 different Ti. So in situations like that, what generally comes handy is a method where you can guess the solution and prove that is correct. Okay, so this method is called guessing the solution. So generally you can do that whenever you have to prove something. So you are given, okay, prove that this is order something, and you say, okay, let me guess the solution and I prove this is correct. So I am giving you this Tn is order n log, and you have to prove this. So how you will start? You will say, okay, I am guessing the solution. So let's say Tn is less than equal to, if it is order n log n, this will be, you can find some a such that this is less than equal to a n log n. Okay, so some a greater than 0. Now, okay, fine, let's do that. Tn less than equal to a n log n. So then I put LHS as it is. I have to prove LHS is less than equal to a n log n, but right now I substitute that in the RHS. So put that in the RHS. Okay. So then, because Ti will be less than equal to a log I, so less than equal to theta n plus 2 by n sigma I is equal to 1 to n minus 1 ai log. So Tn is less than equal to this particular quantity. Sure. Now to solve this, I do some trick. Okay, and you will see why that is needed, because I cannot prove this directly in this form. So what I do, I divide this into 2 parts, from I is equal to 1 to n by 2 and I is equal to n by 2 plus 1 to n minus 1. Okay, so I divide the sequence into 2 parts. So let me just write it. So Tn is less than equal to theta n plus 2a by n sigma I is equal to 1 to n by 2 I log I plus, so I can take this common, sigma I is equal to n by 2 plus 1 to n minus 1 I log I. Okay, I have done nothing. I have taken I is equal to 1 to n minus 1 divided into 2 sequences. But now I will put the less than equal to condition differently on both. Okay. Now can you think of like what this whole sequence will be less than equal to, and similarly what this whole sequence will be less than equal to. And I will try to write something simple. So I will say, okay, in this whole sequence, every term is less than equal to I log n by 2, because doing summation with log quantity like log 1 plus log 2, that is complicated. So I am just replacing by a constant in this whole sequence. Fine. Similarly, this will be also less than equal to I log n minus 1, but I am just writing n. Okay. Sure. So I can write this whole thing less than equal to theta n plus 2a by n. Okay. Now there are two things. So log n by 2 is common. Log n by 2 times, now summation I from 1 to n by 2, and you know the formula for that, that will be n by 2 plus 1 by 2 plus the second term, the log n is common, log n times, and this is summation I is equal to n by 2 plus 1 to n minus 1. Okay. So now what is that? And now this one I will just compute separately. So this will be summation I is equal to 1 to n minus 1 minus summation I is equal to 1 to n by 2. Okay. So that is n times n minus 1 by 2 minus n by 2 plus 1 by 2. Okay. So actually there is 8 common, so by 8, and you will find 4 n square minus 4n. Okay, and this is n times n plus 2 divided by 8, so minus n square minus 2n. Okay, yeah, I hope I have done that correct. So this will be 3n minus 2 divided by, so I am putting this back, so this will be 3n n minus 2 by 8. Okay, sure. So things are not becoming simpler, as you can see, but yeah, we are hoping that this will give us something. Okay, so okay, let's see what we can do now. So this is theta n, we are replacing it by something. Let's say theta n is less than equal to some Cn. So this we are writing as Cn. Okay. So now let's again write this whole thing. So Tn less than equal to Cn plus, okay, so this Tn will be less than equal to Cn plus. Now this term you have to write carefully. Okay, so there is surely this 2a by n. Okay, but inside there is one term with log n by 2, another with log n, right? And I think we can use a trick here. We can replace this log n by log n minus log 2. Okay, so in this case what will happen, this will be log n common, so 2a by n log n, and we have to add this and this. Oh, you will now say that I just got this by subtracting this minus this. Okay, and now I am adding plus sigma I equal to 1 to n by 2. Okay, so I think I can go back to this term and say, okay, this adding this and this will give me this particular term. So this becomes easy. 2a by n log n, this plus this is this one, so that is n times n minus 1 by 2, and this log 2 will be minus, so minus 2a by n log 2, and what will this be? summation of this term, that is n times n plus 2 by 8. Wow. So this is what this Tn looks like. Fine. Let's cancel out terms that do. So I am just writing it in the new page. So Tn is less than equal to, I'm sorry, this is Cn plus a n minus 1 log n minus a n plus 2 by 4 log. Okay, let's try to put the terms separately. So this is same as a n log n plus Cn minus a log n minus a n by 4 log 2 minus a by 2 log 2. So let's put the terms in n together. So this is a n log n plus c minus a by 4 log 2 n minus a log n minus a by 2. Now I have to prove that this whole thing is less than equal to a n log n. Okay, for summing. Now when will this happen? So you see, this is a n log n minus this term minus this term. So if this whole thing also becomes negative, that will be true. And when will this thing be negative? When a is greater than 4c by log. Right? And given is c, because remember what is c? C is for the partition one, so I can find c first. Given c, I can always find a such that this holds true. So I can always find an a. Such that this holds true. So for this particular way, I can prove that Tn is less than equal to a n log n. And once I am able to prove, that means Tn is theta n log n, or order n log n. Okay, so that is how you can prove the average time complexity of quicksort is theta n log n. Now, yeah, this one I think you should go back together and let me know if you have doubts. And as an exercise, okay, so just to convince that whatever tricks we did was important, what you should do, for example, what happens if I do not break into sequences? Okay, I divide into two sequences. What would happen? Or, like, will this work if I try Tn is less than equal to an? This should not work. Okay, so now, but find out what happens. What happens if I try Tn is less than equal to n? This will be just to convince yourself that this will not work if you try something arbitrary that is not correct. This will work if you try something, a correct solution, and guess it, and you can prove that is correct. Okay, sure. So now, so we have seen quicksort. We know what is the average time complexity and what is the worst case complexity. Sure. Now before we move to some other algorithms for sorting, I just wanted to have a few things about sorting. See, whenever you talk about a sorting algorithm, you talk about many things. So one thing you talk about is what is the time complexity. And that we have been seeing. We are seeing quicksort is good, average case, it's good, right? Merge sort is good, even the worst case. So if you want a worst case time complexity of theta and log n, you will go for merge sort. But if you want an average time case complexity, so you can always go for quick sort. Now there are other things like insertion sort and all. They are theta n square. Okay. They are not very good in terms of time. But apart from time complexity, you can also talk about space complexity. Okay, so just so that this term is clear, space complexity. What is the space complexity? That generally takes care of how much memory is required in terms of input size. So how much memory would require? So at least when you are sorting, you will have to read the input values. So it cannot be less than theta n. So theta n is anywhere there. Okay, but so you have to read the inputs. So, but apart from reading the input, yes, you can call it theta n, or you can just say reading the input. Apart from that, how much memory do you need? And that is what determines the space complexity of memory. How much additional? So you can see how much additional memory. Okay. So if this additional memory is order 1, that means you can do it with by only using some variables, not an array of size n. Then you will call it, okay, so if it is order 1, you call it in place algorithm. It's in place. I don't need any extra memory. I only need order 1 extra memory. But if the additional memory is of a function of n, so this is like order n, then this is not an in place. No more an in place algorithm. So generally when you try to design algorithm, you also are interested in getting an algorithm that is also in place in addition to being efficient. So yeah, there are more things. For example, is this a stable sorting? We will discuss this topic in detail later, but just to give you an idea. So what is stable sorting? So suppose you get an input where some elements are repeating. So 3, 7, 6, 6, 2, 5, 5. Right? Things are repeating. Now when you try to sort it in increasing order, so the elements that are same, say these two 6, let's say even say prime and double prime, if the sorting algorithm maintains the same order between the elements having the same key. So in the sorted order, 6 prime comes before 6 double prime, always, then this is stable sorting. Okay. So whenever there are two elements at the same in key value, after sorting they remain in the same order, then this is a stable algorithm. But if the algorithm cannot ensure this, this is not a stable sorting. Okay. So yeah, we will discuss in detail. But what I will like that you try and see for this quick sort and merge sort, where do they stand in terms of being in place? Are they in place? Okay, and are they stable or not? So I want you as an exercise. Okay, think about it. Are these algorithms in place or stable? And if you have difficulties, we will discuss. Okay. Now let's move on to some other interesting divide and conquer algorithm.